Alright, this is lesson 8.4. Unlike other videos, I am going to talk about the do now, and because do now is kind of important, right? Because, well, it says both of these are sound waves, and, well, I want you to describe, well, what do you observe? Well, clearly on the left-hand GIF, you see that the source is not moving, right? So there's a sound source, and whatever is creating these waves is not moving. Whereas on the right hand side, your sound source is moving, right? And you can clearly see that the sound waves kind of look different when something is moving. Now, really, I want you to guys, I'm gonna show you a video. And what you saw, what you see here, like a moving sound source, well, that's something called the Doppler effect, right? So what is that happening here is called a Doppler effect. And I want you guys, and if you recall, uh, if you've ever heard like a fire truck siren or a police siren, kind of police car passing by you, well, the sound as it makes coming towards you is different from the sound that it makes as it moves away from you. Right, and you can kind of hear a difference. And let me jog your memory here, okay? So I'm gonna play this video, and I want you to pay very carefully, very good attention to the sound.
To the siren sound as it approaches compared to after it goes by. Can you hear the difference in the pitch? The sound changes.
So not, we'll watch it again. We'll watch it again, right? Again, while we pay
Listen to
attention
the
to the
siren
sound.
sound as it approaches compared to after it goes by. Can you hear the difference in the pitch?
Right? You can kind of hear some sort of this difference here. I'm not talking about the loudness of the sound, right? We're talking about the pitch, right? Because as it comes towards you, there's some kind of like high pitch, and as it goes away from you, well, it kind of sounds like it's a lower pitch. Let's watch this one because this is, I think this is more noticeable. You definitely do hear a difference in sound, right? As it comes toward you, right? Let's watch it again. As it comes towards you, higher pitch. And then as it moves away from you, it's much lower pitch. So okay, this is called a Doppler effect, right? So what's happening right here is called a Doppler effect, and we're gonna talk about it, and we're gonna talk about why that happens. So let's say, for example, this is a sound, right? This is a sound source. You have a speaker. It's vibrating at 55 hertz, so it's vibrating at 55 times per second. All right. And so now this is a stationary sound wave, right? You can see the sound waves coming out from the source. Now, as you can see here, right, the compression areas, right? So where the parts where the particles are most stuck together, the most compressed areas, they kind of correspond to a crest of a transverse wave, right? If I were comparing longitudinal and transverse waves, well, you would compare the compressed areas to the crest, right? And we know that the distance between the crests is equal to your wavelength, right? So each of these lines, they represent one wave, right? So the distance between each of these lines, they represent a wave. And something very important, right? Because we need to make sure we know that. So this is again. Did I write the? So as a sound source. So again, let's look at this sound source. This sound source is moving towards this observer, right? As the sound source moves towards the observer, what do you notice about the frequency and the wavelength of these sound waves that hit the observer? Well, as right, so you can see that clearly. I'll take a picture of this. I'm gonna show it to you guys. If I can find my pen, yeah. Okay, right here, right here. All right. So you can clearly see, right? The wavelength of these waves are kind of bunched up. Well, it's not really a wavelength. Actually, let me take a better picture. All right. So you see, the sound waves are kind of hitting the observer. They don't have much. They don't have a really large wavelength compared to the other side here. Right. So the wavelength of these waves are smaller, but because you have more wave cycles that occur in a given amount of time, well, you will have a higher frequency, right? So here you have a higher frequency and lower wavelength, which is really just they're inversely proportional, right? If you have a high frequency, you have a lower wavelength. I feel like that kind of makes sense because again, the sound source is moving towards the observer. So yeah, well, and the opposite happens, right? The opposite happens. The opposite holds true when the sound source is moving away from the observer, right? So now the sound waves that the observer is hearing they have a longer wavelength, but because they have a longer wavelength, they have a lower frequency, right? There's not as many sound waves that occur in a given amount of time compared to the other side. So as the sound source is moving away from the observer, you hear a lower frequency of waves. And that's really important because the frequency of your sound determines the pitch of your sound. And so the higher frequency means that you have a higher pitch, which makes sense because as a car or a car horn, a police siren comes towards you, you hear a higher frequency of waves, and therefore you hear a higher pitch. And when they move away from you, you hear a lower pitch because you have a lower frequency of sound waves. And it's very important. And that's why things have a higher pitch and a lower pitch as you have so far observed in real life. Now this is just summary, right? So sound waves moving towards higher pitch, higher frequency, lower wavelength, and vice versa. If you're moving away, lower pitch, lower frequency, higher wavelength. So as a car approaches a pedestrian, right? So as a car approaches pedestrian, the driver blows his horn. Compared to the sound emitted by the horn, the sound wave detected by the pedestrian has a 1. So the car is moving towards pedestrian, right? So your sound source is a car, and you have a stationary pedestrian. So the sound source is moving towards the pedestrian. So as you're moving towards someone, you have a higher frequency and a lower wavelength, okay? And therefore, we know that frequency is related to pitch. So you have a high frequency, you have a high pitch. All right, so the answer here is B. All right. Now this one might be a little bit harder. So the horn of a car produces a sound wave of constant frequency. The car traveling at constant speed approaches, passes, and then moves away from a stationary observer. Which graph best represents the frequency of the sound wave detected by the observer during the time interval in which a car approaches, passes, and moves away? And now you'll have to realize that if we go back, so again, it's approaching, passes, and moves away. This is very important because so if you're approaching, passing, if you're approaching, you have a high frequency. If you once you move away, you have a lower frequency, which means that A and D cannot be correct, right? Because you're moving from a high to a lower frequency. So you're left with B and C now. Right? You're left with B and C. Now, have to realize the frequency of your waves, the wavelength of your waves are constant if you're moving at a constant velocity, which in this question you are. This is very important. Your frequency does not change if your sound source is moving at a constant velocity, either going towards or away. You'll see on the top GIF that the wavelength in between each wave cycle is the same, which means your frequency also will be constant. And the same goes for when the sound source is moving away. Which means the only answer here is C, because B is saying that your frequency is constantly decreasing. Right, so constantly decreasing would kind of look like this, right? So you're gradually increasing you're gradually decreasing the frequency of your waves, and the wavelength gets longer and longer. This graph C is saying that, well, your frequency is high and the wavelength stays the same. Well, I'm not really drawing it too well. Right, so your wavelength stays the same up until the point you cross the observer, and then once you're moving away, well, then your wavelength, your frequency will be lower, but your frequency is constant. Your frequency is constant, you have the same wavelength. Whereas B is saying that your frequency gradually decreases over time. So C is the correct answer here. But give you some time to read it. Feel free to pause, right? Feel free to pause at any given time to see if you can attempt this question yourself. All right? Again, feel free to pause at any single time because I will move on and we'll solve the question with you. So in the diagram below, a stationary source located at point S produces a sound having a constant frequency of 512 Hz. Observer A is 50 meters to the left of S, and here's a frequency of 512 Hz. Observer B, 100 meters to the right of S, here's a frequency lower than 512 Hz, right? So lower. So A here is the same, 512, and B here is a lower frequency. So if A is hearing the same frequency as at point S, well, A is not moving. It's hearing the same exact frequency. A is not moving. So A is stationary. So you're left with C and D. And if B is hearing a lower frequency, well, that must mean that observer B is moving away from point S. Moving away. All right. So you have to be moving away to have a lower frequency. All right. So 4 when the sound waves hits stationary. Yeah. So I think these two GIFs are very self-explanatory. You'll see in the top GIF that, well, now the sound source is stationary, but the observer is the one that's moving. And each time the smiley face lights up, well, that eventually means that, well, now you have that sound wave is hitting the observer. So the observer is hearing that sound wave. You'll notice as the observer moves towards the source, as located in the top GIF, as the observer moves towards the source, well, it lights up more, which means that he's hitting more sound waves per second. And if you're experiencing more sound waves in a given amount of time, well, you have a higher frequency. And therefore, here you hear a higher pitch. Vice versa, if your observer is moving away, well, you hear less sound waves per second and you have a lower frequency, right? You hear a lower frequency of sound waves. So let's do a practice problem. All right, so feel free again to pause at any given time to see if you can do this yourself. So an astronaut is traveling towards Earth. All right. So an astronaut is traveling towards Earth in a fast-moving spacecraft, receiving a radio signal. And again, a radio signal is a radio wave. It's a wave. Might not be a sound wave, but a radio signal is a wave. So as you're moving towards Earth, right, that means you're hitting more waves per second, which means you have a higher frequency. And because frequency and wavelength are inversely related, well, then that must mean you have a shorter wavelength. All right, let's do this one. So again, pause if you want to solve this yourself. So system contains, emits, and the most important part of this question here is that compared to the 1000 hertz frequency emitted by the speaker, or rather, no, that's not the most important part. The most important part is this one. The microphone is moved at constant speed from the 0.5 meter position, which is over here, back to its original position 1 meter from the speaker. So you're moving away from the speaker. So if you're moving away from the speaker, you will have a lower frequency. All right.